Welcome to this video where we will be solving LeetCode problem number 2198, titled Number of Single Divisor Triplets. In this problem, we are tasked with finding the count of valid triplets in an array based on specific divisor conditions. Stay tuned as we break down the problem and explore efficient approaches to solve it. The problem we're tackling is called Number of Single Divisor Triplets. Here's the setup. You're given a zero-indexed integer array called nums. A triplet, denoted as I, J, K, is considered valid only if two conditions are met. First, the indices must satisfy the relationship 0 equals I less than J less than K nums.length, meaning the indices are distinct and ordered. Second, the sum of the three elements at these indices, that is nums, I, plus nums, J, plus nums, K, must be divisible by exactly one element within the triplet. Your task is to return the total number of such valid triplets. The input is simply an array of integers, and the output is a single integer representing the count of valid triplets. Keep these requirements in mind as we explore some examples to clarify the problem further. Let's take a look at the first example. Here, the input array is nums equals 4, 6, 7, 3. The output is 3, and here's why. There are three valid triplets in this array. First, for the triplet, I equals 0, J equals 1, K equals 3, the sum of the elements is 4 plus 6 plus 3 equals 13. In this case, only nums, 3, equals 3 divides the sum. Second, for the triplet, I equals 0, J equals 2, K equals 3, the sum is 4 plus 7 plus 3 equals 14. Here, only nums, 0, equals 4 divides the sum. Lastly, for the triplet, I equals 1, J equals 2, K equals 3, the sum is 6 plus 7 plus 3 equals 16, and only nums, 1, equals 6 divides this sum. Since these are the only triplets meeting the conditions, the result is 3. No other combinations satisfy the divisibility requirement. Now consider the second example with the input array nums equals 1, 2, 2. In this case, the output is 0. This is because there are no valid triplets in the array. For every possible triplet, I, J, K, the sum of the elements fails to meet the condition of being divisible by exactly one of the triplet elements. As a result, the total count of valid triplets is 0. In the third example, the input array is nums equals 3, 2, 5, 8, and the output is 1. Here, we find only one valid triplet. For the triplet, I equals 0, J equals 1, K equals 2, the sum of the elements is 3 plus 2 plus 5 equals 10, and only nums, 2, equals 5 divides this sum. No other triplets in the array meet the criteria, so the total number of valid triplets is 1. Remember, the key is that the sum must be divisible by exactly one of the elements in the triplet, and this is the only case where that happens. Finally, let's review some constraints and edge cases to consider. The length of the array, nums.length, is guaranteed to be at least 3 and at most 100. Each element in the array falls within the range of 1 to 100. Important edge cases include scenarios where the array contains duplicate elements, where all elements in the array are identical, or where the triplet sum does not meet the divisibility condition for any triplet. Another edge case is when the triplet sum is divisible by more than one element in the triplet, which would disqualify it as a valid triplet. These constraints and edge cases will guide you as you develop your solution. To solve problem number 2198, number of single divisor triplets, we need to count all valid triplets, I, J, K, such that the indices satisfy the condition 0 equals I less than J less than K nums.length. Additionally, the sum of the three elements, nums, I, plus nums, J, plus nums, K, should be divisible by exactly one of the elements in the triplet. This means we need to carefully evaluate both the divisibility condition and ensure that only one of the three elements divides the sum. Since the problem involves identifying and validating triplets, we need an efficient strategy to minimize redundant checks while maintaining accuracy. Let's review the approaches that were considered to tackle this challenge effectively. The first approach is the brute force method. Here, we use three nested loops to iterate over all possible triplets, I, J, K. For each triplet, we calculate the sum of the three numbers and check divisibility against all three elements of the triplet. While this method is simple and guarantees correctness, its time complexity is O(n)^, making it computationally expensive. This approach becomes infeasible for large input arrays due to the sheer number of combinations to examine. Next, we have the optimized approach using frequency count. Instead of iterating over all triplets, we use a frequency array to track the occurrences of each number in nums. We then iterate over unique combinations of numbers to calculate their sums and check divisibility. This reduces redundant calculations and improves efficiency. The time complexity is n squared in the worst case, but this is significantly better than the cubic complexity of brute force. This approach is particularly advantageous for arrays with repeated numbers, though it requires more careful implementation. Finally, there's the hashing-based approach. Here, we use a hash map to store the count of each number and iterate over all pairs, nums I, nums j. By computing the sum for each pair and checking divisibility using the hash map, this method avoids directly iterating over all triplets. Its complexity is similar to the frequency count approach, n squared, in the worst case, but its implementation is slightly more complex due to edge cases, like handling zero divisors and ensuring triplets are unique. Among these methods, the optimized approach using frequency count was chosen as the most practical solution. The key insight here is that instead of iterating over every triplet, we can focus on unique combinations of numbers by leveraging frequency counts. This reduces redundant checks and simplifies computation. To ensure a triplet sum S is valid, it must be divisible by exactly one of the elements in the triplet. By pre-computing sums and utilizing frequency counts, we can verify this condition efficiently. This approach offers a good balance between simplicity and performance with a time complexity of n squared. While the brute force method guarantees correctness, its n cubed complexity makes it unsuitable for large inputs. The hashing-based alternative, though effective, requires careful handling of edge cases and is slightly more complex to implement. Thus, the frequency count approach stands out as a clear winner, combining clarity, efficiency, and scalability for solving this problem effectively. To solve the problem of finding the number of single divisor triplets, we first need to fully understand the input and the problem requirements. We are given an array nums that contains integers, and our goal is to identify all triplets, I, j, k, such that the indices satisfy 0 equals I less than j less than k nums.length. Additionally, the sum of the triplet, which is nums I plus nums j plus nums k, must be divisible by exactly one of the elements in the triplet. This condition is critical to solving the problem correctly. However, since the array size can go up to 1000, a naive brute force approach with a time complexity of n cubed would be too slow. Instead, we need to design an optimized algorithm that respects these constraints while maintaining efficiency. Now, let's delve into the key observations that drive our approach. The sum of any triplet can be expressed as S equals nums I plus nums j plus nums k. For the condition to hold, S must be divisible by exactly one of the three elements in the triplet. This means that if S is divisible by one element, it should not be divisible by the other two. For instance, we might have a scenario where S%nums I equals 0 but S%nums j equals 0 and S%nums k equals 0, or any other permutation of this setup. To efficiently handle these cases, we can use a frequency map to store the count of each unique number in nums. This allows us to reduce redundant computations by focusing only on unique values rather than repeatedly processing duplicates. The first step involves creating this frequency map. For example, if nums equals 1, 2, 2, 3, the frequency map would be 1, 1, 2, 2, 3, 1. After creating the map, we extract the unique values and sort them. Sorting ensures that we systematically generate triplets in ascending order. For the earlier example, the unique values would be 1, 2, 3. With the unique values sorted, we can now iterate through all possible combinations of triplets, A, B, C, using these unique values. For each triplet, we calculate the sum S equals A plus B plus C and check whether S is divisible by exactly one of the three elements. To do this, we count how many of the conditions S% A equals 0, S% B equals 0, and S%C equals 0 hold true. If exactly one of these conditions is true, the triplet is valid. Additionally, since duplicates may exist in the original array, we need to account for their frequencies. For example, if the triplet is 2, 2, 3, and the frequency of 2 is 2 and 3 is 1, the total count of such triplets would be 2 asterisk 2 to 1 / 2 asterisk 1. This formula ensures that we consider all combinations of the triplet while avoiding double counting. Finally, we accumulate the total count of valid triplets by summing up the contributions of all valid combinations. It's also important to handle specific edge cases, such as arrays with fewer than 3 elements, where no triplets can be formed, or arrays with all identical elements, where the condition fails as s%x == 0 for all triplet elements. Using the frequency map helps to keep the algorithm efficient, even for large arrays with many duplicates. There are a few key insights that make this approach both correct and efficient. First, the divisibility check is the core of the problem, as we need to ensure that S satisfies the condition of being divisible by exactly one of the triplet elements. This requires careful tracking of how many divisors exist for a given triplet sum. Second, the frequency map is a crucial optimization. By storing the count of each unique number, we avoid recomputing counts for duplicates and significantly reduce redundant work. Sorting the unique values is another important step, as it ensures we generate triplets systematically and avoid unnecessary computations. For handling duplicates, we use combination formulas to determine the number of ways elements can form valid triplets, accounting for their frequencies. Together, these insights ensure that the algorithm is both efficient and scalable. The primary data structures involved are the frequency map, which is typically implemented using a dictionary or hash map, and the sorted list of unique values, which allows for systematic iteration. Finally, let's analyze the complexity of this approach. Constructing the frequency map requires O(n) time, where n is the size of the array. Sorting the unique values takes O(m log m), where m is the number of unique values in nums. Iterating through all combinations of triplets formed by these unique values has a time complexity of O(m cubed). Combining these, the overall time complexity is O(n plus m log m plus m cubed). In terms of space complexity, we use the frequency map and the sorted list of unique values, both of which require O(m) space. Here, m is generally much smaller than n if there are many duplicates in the array. This balance between time and space complexity ensures that the algorithm remains efficient, even for the upper bounds of the problem constraints. This solution finds the number of single divisor triplets in the given array, following the problem's constraints. We use the itertools.combinations method to generate all unique triplets, A, B, C, from the array where A, B, and C are distinct. For each triplet, we calculate the sum of its elements, total equals A plus B plus C, and check how many of the three numbers divide this sum exactly. To do this, we use the modulo operator, total%x == 0, for each number in the triplet. If the sum is divisible by exactly one of these numbers, tracked using the divisible_count variable, it qualifies as a valid triplet, and we increment the count. At the end, the total number of such valid triplets is returned. This approach has a computational complexity of O(n) cubed, due to the triplet generation and divisibility checks, making it suitable for small input sizes. Here, we begin with the Java implementation of the solution by importing the necessary utilities and defining our class, solution. Inside it, we declare the method SingleDivisorTriplets, which takes an integer array nums as input and returns the count of triplets meeting the problem's criteria. We initialize a variable count to 0, which will store our result, and n to store the length of the array for convenience. Next, we use 3 nested loops to iterate through all possible triplets in the array with indices I, j, and k, ensuring the condition I less than j less than k is met. Within the innermost loop, we extract the 3 elements of the triplet, A, B, and C, and calculate their sum, total. We then initialize a variable divisible count to 0, which will track how many of the triplet elements divide the total evenly. Using simple modulo checks, we increment divisible count for each element of the triplet that divides the sum without a remainder. For example, if total%A = 0, we increment divisible count by 1, and we do the same for B and C. Finally, after checking divisibility for all 3 elements in the triplet, we evaluate if the divisible count equals 1, meaning only one of the triplet elements divides the sum. If this condition is satisfied, we increment our count variable. Once all triplets have been processed, the nested loops end, and we return the value of count, which represents the number of valid triplets that meet the problem's criteria. This implementation ensures that every possible triplet is checked, and the conditions are accurately applied to determine whether the triplet satisfies the requirements. In this example, we are given the input array nums equals 1, 2, 3. We start by initializing a variable count to 0, which will keep track of the number of valid triplets. Next, we generate all unique triplets from the array using combinations, ensuring that the triplets are in the form A, B, C, or A less than B less than C. For this input, there's only one possible triplet, 1, 2, 3. Now, we calculate the total of the triplet, which is 1 plus 2 plus 3 equals 6. We also initialize another variable, divisible_count, to 0 to track how many elements in the triplet divide the total evenly. Checking each element, we see that 6% 1 equals 0, so we increment divisible_count to 1. Similarly, 6% 2 equals 0 and 6% 3 equals 0, bringing divisible_count to 3. Since divisible_count is not equal to 1, this triplet is deemed invalid, and we move on without modifying the count variable. With no valid triplets found, the count remains 0, so we return count equals 0 for this example. Now, let's move on to the next example with the input array nums equals 4, 6, 8, 10. Starting again, we initialize count equals 0 to track valid triplets. Using combinations, we generate all unique triplets where A less than B less than C. For this array, the possible triplets are 4, 6, 8, 4, 6, 10, 4, 8, 10, and 6, 8, 10. We'll evaluate each of these triplets to check if they meet the criteria for being valid. Let's process the first triplet, 4, 6, 8. The total of this triplet is 4 plus 6 plus 8 equals 18, and we initialize divisible_count to 0. Checking divisibility, 18% 4 equals 0, so divisible_count remains 0. However, 18% 6 equals 0, so we increment divisible_count to 1. Lastly, 18% 8 equals 0, leaving divisible_count at 1. Since divisible_count equals 1, this triplet is valid, and we increment count to 1. Next, for the triplet 4, 6, 10, the total is 4 plus 6 plus 10 equals 20. Starting with divisible_count equals 0, we find that 20% 4 equals 0, so we increment it to 1. Then, 20% 6 equals 0, and 20% 10 equals 0, bringing divisible_count to 2. Since divisible_count is greater than 1, this triplet is invalid. Finally, for the triplet 4, 8, 10, the total is 4 plus 8 plus 10 equals 22. Checking divisibility, none of the elements divide 22 evenly, so divisible_count remains 0, making this triplet invalid as well. The last triplet to evaluate is 6, 8, 10. The total is 6 plus 8 plus 10 equals 24, and we start with divisible_count equals 0. Here, 24% 6 equals 0, so we increment divisible_count to 1, while 24% 8 equals 0 and 24% 10 equals 0 leave divisible_count unchanged. Since divisible_count equals 1, this triplet is valid, and we increment count to 2. With all triplets processed, we find that the valid triplets are 4, 6, 8, and 6, 8, 10. Thus, the final value of count is 2, and we return count equals 2 for this example. In this example, the input array is nums equals 5, 7, 11. As always, we initialize count equals 0 to track valid triplets. Using combinations, we generate the only possible triplet, 5, 7, 11. For this triplet, we calculate the total as 5 plus 7 plus 11 equals 23 and initialize divisible_count to 0. Checking each element, we find that 23% 5 equals 0, 23% 7 equals 0, and 23% 11 equals 0. Since none of the elements divide the total evenly, divisible_count remains 0, making this triplet invalid. Since no valid triplets were found in this example, the count remains 0. Therefore, we return count equals 0 as the final output for this input. With this, we've completed evaluating all examples, and the solution approach should now be clear. Let's break down the time complexity of the given solution. First, the code uses the combinations function from the itertools module to generate all unique triplets of size 3 from the input list nums. The number of these triplets is determined by the binomial coefficient c, n3, which is equal to n times n1 times n2 divided by 6. This means that generating the triplets has a time complexity of n cubed. Next, for each triplet, the code performs a few constant time operations. It calculates the sum of the three elements, which is an O1 operation, and then checks the divisibility of the sum by each of the three elements, which involves three modulus operations. Since each of these is also O1, processing a single triplet remains O1. Combining these steps, we can analyze the total time complexity of the function more thoroughly in the next part. To determine the overall time complexity, we consider the number of triplets and the operations performed on each. Since there are n cubed unique triplets and processing each triplet involves O1 operations, the overall time complexity becomes n cubed multiplied by O1, which simplifies to n cubed. Now, shifting focus to space complexity, the memory usage is influenced by a few key factors. First, the input list nums requires n space, where n is the number of elements in the list. Then, there are temporary variables like count, a, b, c, total, and divisible_count. These are all scalars, meaning they require constant memory, or O1 space, regardless of the input size. We'll now evaluate other memory considerations to finalize the space complexity. When we look at how combinations are generated, the itertools.combinations function is particularly efficient because it generates triplets lazily, one at a time. This means it does not pre-compute or store all combinations in memory, ensuring that the space overhead for combination generation is O1. Additionally, the algorithm does not make use of any auxiliary data structures like arrays or hash maps that scale with the input size. The absence of such structures further minimizes memory usage. Combining these factors, the overall space complexity is determined to be n, which is dominated by the input list nums. This efficiency in space usage complements the algorithm's design, even though the time complexity remains a limiting factor. When analyzing best, average, and worst-case scenarios, the time complexity remains consistent across all cases due to the algorithm's structure. In the best case, the algorithm still iterates over all possible triplets, resulting in a time complexity of n cubed. Similarly, the average case involves the same number of combinations and operations, so it also remains n cubed. Lastly, in the worst case, the algorithm must process all possible triplets, which again results in n cubed. Comparing this approach to a brute force method, both have the same time complexity of n cubed. However, using itertools.combinations simplifies the code and avoids manually implementing nested loops. To optimize further, techniques like sorting the array or applying mathematical properties could help reduce the number of triplets that need to be processed, potentially improving performance. To conclude, the current solution has a time complexity of n cubed and a space complexity of n. While this approach is manageable for smaller input sizes, it becomes computationally expensive as the size of the input grows. Any optimization would need to focus on reducing the number of triplets processed or applying mathematical insights to minimize operations. Such improvements could make the algorithm more practical for larger datasets, ensuring better scalability without sacrificing correctness. When solving this problem, there are a few common mistakes to watch out for. First, it's crucial to remember the condition that the sum of the triplet must be divisible by exactly one element. If you accidentally include cases where the sum is divisible by more than one element, it violates the constraints and leads to incorrect results. Next, handling duplicates in the array is another frequent issue. If the array has duplicate numbers, you might accidentally count the same triplet multiple times, inflating your results. You can address this by using sets or carefully avoiding repeated counts during your iteration. Another pitfall is using a brute force approach. While it might seem intuitive to check all combinations of triplets, an n cubed solution will quickly become impractical for larger inputs. Instead, you'll need to optimize using techniques like frequency arrays or leveraging mathematical properties to eliminate redundant calculations. Additionally, ensure your divisibility checks are correct. For example, Directly checking if the sum modulo a number is 0 without confirming that the number isn't 0 can lead to runtime errors like division by 0. Finally, don't overlook array bounds. Your iteration logic must respect the requirement that indices I, j, and k satisfies 0 less than or equal to I less than j less than k to avoid processing invalid triplets. Now, let's focus on interview strategies to tackle this problem effectively. One of the most critical aspects is demonstrating a solid understanding of the divisor constraint. Clearly explain how you ensure that the sum is divisible by exactly one element, as this is the core logic and a common area where errors occur. Another key point is optimization. For larger inputs, using frequency maps or arrays to pre-process the data can drastically reduce redundant calculations, making your solution more efficient. Interviewers often appreciate seeing this kind of optimization. You should also be prepared to handle edge cases. For instance, if the array is empty, has fewer than 3 elements, or includes many duplicates, your solution should account for these scenarios gracefully. Showing awareness of these edge cases highlights your attention to detail. Additionally, discuss trade-offs in your approach. For example, while using a frequency map improves time complexity, it does require additional space. By explaining these trade-offs, you demonstrate your ability to think critically about the balance between time and space efficiency. Expanding your understanding of this problem can be helpful, and exploring related problems is a great way to do that. For instance, LeetCode 15, the three-sum problem, involves finding unique triplets that sum to 0. While it doesn't have the divisor constraint, the logic for enumerating triplets is similar, making it a good practice problem. LeetCode 18, or foursum, builds on this idea by extending the concept to quadruplets, which helps you practice higher-order combinations. Another interesting problem is LeetCode 16, threesum closest, where the goal is to find a triplet whose sum is closest to a target value. This requires careful handling of combinations and is excellent for sharpening your precision. Lastly, there's LeetCode 1985, which involves finding the kth largest integer in an array. Although it's not directly related to triplets, it emphasizes efficient data handling and optimization, skills that are transferable to pre-processing and divisor-related problems. There are multiple approaches to solving this problem, each with its own trade-offs. A brute force method, which has a time complexity of O(n cubed, is the most straightforward. It involves checking all possible triplets to see if they meet the divisor condition. While this approach works for small inputs, it quickly becomes inefficient as the input size grows. A more optimized solution uses a frequency map to pre-process the array. This reduces redundant checks and brings the time complexity down to O(n squared, which is much more practical for larger arrays. Another efficient method involves sorting the array and leveraging the two-pointer technique. Sorting simplifies the logic for maintaining the order of indices I, j, and k, while two pointers help you find valid triplets efficiently. However, you need to take extra care to handle duplicates properly in this approach. For advanced scenarios, you might consider bit masking. This technique can represent subsets of the array and perform faster checks, but it's typically unnecessary unless the problem explicitly calls for it. Each approach has its strengths, and choosing the right one depends on the input size and constraints. Thanks for following along. To summarize, we explored how to solve LeetCode problem number 2198 using an optimized approach to count specific triplets. We discussed important concepts like divisor properties and efficient iteration. If you enjoyed this video, don't forget to like and subscribe for more problem-solving content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!